We didn't have
Tuesday I wasn't here,
Yeah,
so let's see.
Tuesday.
X squared minus 4x. So this is the problem from yesterday over x minus 2. And then on this, I had done division and noted that you could rewrite it as x minus 2 plus 1 over x minus 2. And the derivative of that is slightly easier. F prime of x, we calculated last week to be x squared minus 4x plus 3 over x minus 2 squared. If you go with the alternate definition, you get 1 minus 1 over x minus 2 squared. And we calculated critical values. And this was, I think, oh, was it yesterday? This is where I started to lie to you. It must have been yesterday. Okay. I came to me in a dream that I lied. We found the critical values here from the numerator were 1 and 3. However, since the derivative is undefined, we do have to consider that too, even though it's not in the domain of the function. So we do have to consider 2 as a critical number.
We do?
Yeah, for increasing and decreasing. Yeah, because 2 isn't in the domain, it can't be a max or a min, but it will affect when the function, the function could change sign. Sorry, the derivative could change sign around it. So it could change increasing, decreasing.
So we have
So Sila asked if we should do a test point on each side of that, and I said no, and that was a lie.
So we have to consider it a critical.
We have to consider a critical point when we're looking at increasing and decreasing intervals. Okay. Yeah. So even though it's not going to be a max or a min, we still need to consider it for increasing and decreasing. I'm going to take this a step farther today. We're also going to calculate the second derivative. We're going to use the alternate version to do so because it's easier. Okay. So with the alternate version, I could write that as 1 minus parentheses x minus 2 to the negative 2. Makes it pretty easy to consider. So for the of 1 is 0, so I'm going to get 0 minus, and then I'm going to get a negative 2 that comes down, and then x minus 2 to the power negative 3. So altogether, negatives cancel. Drop this into the denominator, and I get that. So the main reason I'm going to use this is for the second derivative test, which is used for checking maxes and mins. So I'm just going to apply the second derivative test here. And the second derivative test applies to your critical values. Now here, I really only care about the critical values 1 and 3, because I'm testing for the second derivative test for max and min. So apply second derivative test for max / min. And why do we know 2 is insignificant for a max or a min? Because it's not in the domain, it leads to an asymptote. And we'll explore the asymptote some more in a minute. It's section 6 is about asymptotes. So what I want to know is what is the second derivative evaluated at 1, because 1 is a critical number. And what is the second derivative evaluated at 3? Because 3 is a critical number. And although you could plug 2 in, you get no answer, so it doesn't help anything. So if we plug that in, what do we get? If I plug a 1 here, I get 1 minus 2 is -1, cube a -1, and you get a -1. So I get -2. Since it's less than 0, this thing must be concave down there. If it's concave down, do I have a max or a min here? Max. Good. Okay. And the max is going to be whatever f of 1 is, which I still need to calculate. Okay. All right, so then this 1 over here, I plug in 3. 3 minus 2 is 1. 1 cubed is 1. So I get 2, which is positive. That means the function must be concave up there. If it's concave up, then I must have a min. And the min is going to be whatever the value of f of 3 is. So now we have to plug in and make those calculations to figure out what the max and min are. So we've got the function right here. Let's do it. So let's see, if we plug in a 1, we're going to get 1 minus 4 plus 5 over negative 1, which gives me negative 2. Is that right?
Yeah.
Coincidence. So the max, relative max of the function is y equals negative 2. As far as the min is concerned, we got to plug in 3. So what are we going to get? Running out of room here. 9 minus 12 plus 5 over 1. What's that come out to? 2? Yeah. Wow, look, another coincidence. So that equals 2. And so next we need to brand these things as relative or absolute, and so to do that, more analysis needs to be made, because the only way to tell if it's an absolute max is if it is the highest y value in the entire domain. Okay, you think negative 2 is the highest y value in the entire domain? No, because here we can see we have a higher y value right next to it, right? And do you think 2 is the lowest number in the whole, based on the whole domain? Answer is no, because there's a lower number over there. So these, we have enough evidence to say they're relative mins and relative maxes. All right, so let's throw a few more pieces of information in here. So we know the domain of this function is all real numbers but 2. Oh, pen, come back here. Oh boy. Uh-oh, maybe my battery died. Huh, all right, let's switch magic boards. So the domain would be from negative infinity to 2, union 2 to infinity. At 2, what happens though? So there's some claim about an asymptote there. So asymptotes are covered in section 4.6. So we're going to get a jump start on 4.6 today, even though I'm not quite done with 4.5. So there are multiple kinds of asymptotes. Vertical asymptotes happen as x approaches some real number from the right or the left. So here, let's take a look at the limit as x approaches 2, and we'll go with the right side of our function, which is what, x squared minus 4x plus 5, thank you, all over x minus 2. So a problem that I have here is I can't just cheat and plug in 2, so we've got to do a numerical evaluation on this. Okay. So what do I know right now? I know that the x value I'm picking is greater than 2 because I'm on the right side. Agreed? But it's close to 2. So if I'm close to 2, x minus 2, the denominator, is going to be greater than 0. Right? Okay, so that's good to know. The denominator is some positive number. Other thing is I'm close to 2, right? So that means if I'm close to 2, this difference must be very small. Right? So what does my fraction look like here in my limit? Well, I have a very small positive number in the bottom. What's the numerator look like? Well, the numerator is pretty close to 2. So let's see, if I take 2 squared, if I take it, let's just make believe it's 2 for a minute. Okay. So, oh, you're alive, thank goodness. I was getting ready to come track you down. Welcome. You know what it's like. So let's see, what's the numerator going to be if we're close to 2? 1? Close to 1?
Yeah. Yeah.
Okay. So if we take a number that's perpetually close to 1 and we divide by a number that's getting smaller and smaller and smaller and smaller and smaller, what's going to happen here?
It's going to get closer to 0.
It's going to get bigger and bigger and bigger and bigger. Yeah. So as x, oops, that's supposed to be an as x heads towards 2 on the right side, y is heading toward infinity. Okay. Positive infinity, because 1 is a positive number, the denominator is a positive number. Okay. So I do have a vertical asymptote on the right side. That asymptote would be x equals 2. Squeeze that in here by shrinking this stuff a little bit. Let's see, how do I do that? Edit, select all, shrink. So we have a vertical asymptote on the right. That asymptote is x equals 2. On the left side, what's the only difference going to be in this situation?
Negative.
So the denominator is going to be negative because I'm going to be on the other side of 2. So on the other side is going to go to negative infinity. But x equals 2 is still that asymptote, right? And sometimes a function will grow up toward its asymptote. Sometimes it'll go in each direction. It just depends on the function. Okay. All right. Other kinds of asymptotes. Brief intermission. We'll come back to this function. Horizontal asymptotes. And you probably went over this in a pre-calculus class. I just want to review some of the basics there. One kind of horizontal asymptote would be y equals 0. That's a horizontal asymptote. And that's going to happen in situations, if it's a rational function, where the degree of the denominator is bigger than the degree of the numerator. Other things that happen, it could be some other constant besides 0. If the degree of the denominator equals the degree of the numerator. We'll take a look at that case in a little bit. So those are the only times you're going to get a horizontal asymptote. There are other kinds of asymptotes besides vertical and horizontal. Does anybody remember one?
Slant.
It could be like, well, like y equals this. It could be a slant or oblique asymptote. Yeah. So another option is what's called a slant or oblique asymptote. And that's going to happen if the, let's see, the degree of the numerator, let's see, how do I want to phrase this? Yeah. The degree of the numerator is 1 more than the degree of the denominator. You get a slant asymptote. Have we seen a function recently where the degree of the numerator is 1 more than the degree of the denominator?
Yes.
The one we're looking at right now. So let's take a look at that again. So our function, f of x, is equal to x squared minus 4x plus 5 over x minus 2. And to discover the slant asymptote, you just do division. Long or synthetic, which I did the other day, and I found this was x minus 2 plus 1 over x minus 2. And the way to think about this is horizontal and slant asymptotes happen as x gets big. So if I consider the limit as x gets big positively of this function, I'm going to write it in the second form. What's going to happen here is this fraction over there is going to be 1 over a bigger and bigger and bigger number, like 1 over 1,000 and 1 over 1,000,000 and 1 over 1,000,000,000, which means it is heading toward, other way, 1 over infinity, which would be
Negative.
non-negative infinity.
0?
0, yeah, 1 over a big number is getting close to 0, right? Yeah, so this thing is going to 0, which means this thing dominates for big x values. So if I zoom out, it's going to look like the line y equals x minus 2. Okay, and we'll check that out in Desmos. So then I think the slant asymptote must be y equals x minus 2. All right, so Desmos and a piece of graph paper, which is kind of going to be one and the same for me here. Hopefully I can see the whole function. We'll see. How do I want to do this? I know. I'm going to steal this and see if I can draw it before I ask Desmos to do so. All right, so what do we know about this function? We know it has a vertical asymptote where?
X minus 2 equals 1.
X equals 2. Okay, so it's not bad. And then we also know as a slant asymptote, y equals x minus 2. So that would be right through here. I think I got that close enough. So the function has to sit between these two lines somehow. Now we also know that this function has a relative max at the point 1, -2. Does that sound right?
Mm-hmm.
So 1, -2, that's right here, isn't it? Yeah. And it has a relative min at 3, 2. True? So 3, 2, I believe, is about there. We looked at the vertical asymptote, and as x headed to 2 from this side over here, it headed up toward the asymptote, vertical asymptote like that. And on the other side, it drops down toward it like that. Okay. Can a function cross a slant asymptote? Answer is yes, it can, turns out. You can't cross a vertical one because that's a domain issue. Okay. But I think you'd have to plot some points to double check that this thing is probably going to stay within the boundaries. But a function could go to the other side of the asymptote and then head back toward it. It's a possibility.
So how come they can cross a slant asymptote but not a vertical or horizontal?
Turns out function can cross a horizontal asymptote also.
Okay, so why can't they cross a horizontal or a
So
vertical?
the reason for a vertical asymptote is it's a place in the function is undefined.
Okay.
So you can't plug that number in it.
Okay.
If you cross this line, that means you plugged in 2 and you got an answer.
Okay.
But that's not going to happen. Yeah. So the rule goes is you can never cross a vertical asymptote because it's also a domain issue. But who knows what can happen with slant and horizontal asymptotes? Functions can wiggle around them a ton of times. Can you imagine that?
I want proof.
All right. You want proof? I can show you a picture proof right now.
Yes.
Yeah, think of a sine. If you take the sine of x and then divide that by x, then you're going to get a function. If I change the window here, let's go y from -1 to 1, and then let's let x go on for a while. Yeah, so this function is going to have a horizontal asymptote that is the y-axis, and it wiggles around it the whole time. So it touches the asymptote infinitely many times. To see what's happening here, the sine of x is basically being squeezed by the function 1 over x and the function -1 over x. It's always trapped between it. Isn't that cool? And it's just stuck wiggling in between it forever and ever and ever. That's kind of cool, isn't it?
Isn't there a flow oh, that.
So 1 over x is always above y equals 0, and -1 over x is always below. However, 1 over x and -1 over x, as x gets big, are both trying to get close to y equals 0. If I take the sine and divide by x, then I force it to be squeezed in between them forever. Yeah, so here's an example where a function crosses its horizontal asymptote infinitely many times. So we have this squished wave. Isn't that awesome?
Yeah.
Yeah. All right, so let's get rid of those suckers and then look at ours. So back home. So let's see how I did for graphing that. F of x equals x minus 2 plus 1 over x minus 2. There's our function, and it's trapped in between x equals 2 and y equals x minus 2. All right, so other things to consider. In this region right here, is the function concave up or concave down?
Concave down.
And in this region over here?
Concave up.
Concave up. Now, often when a function switches from concave up to concave down, there's an inflection point, a point at which the change happens. But what's the problem here?
The inflection point doesn't exist.
Yeah, the inflection point doesn't exist because 2 is the place it changes and 2 is not in the domain. We have this asymptote we can't cross.
So there's not an inflection point?
So there's no inflection point here, even though we change concavity. That happens. So many things can happen. So quick review of that idea right here. Our function again, f of x equals x squared minus 4x plus 5 over x minus 2. Its second derivative, oosh, what was that? It's 2 over x minus 2 cubed. Is that right?
Yeah.
Okay. So what I want to do is I want to pick a couple of points and test what's happening as far as concavity goes. Oops, So we could change concavity around x equals 2. Now we saw the graph, we know it does change. So a nice number on the left side.
1.
That was 0. Yeah, I mean 1's nice too, but 0 is nicer. So if I plug into the second derivative 0, I get 2 over 0 minus 2 cubed. A negative number cubed is negative, positive over negative is negative. So this is less than, oops, wrong direction. This is less than 0 is all I care about. Less than 0 means it is concave down in that region. Do I have to test the other side? Or should I just assume it changes? You have to test because it can be uniform. So f double prime of 4. Sure. I would have picked 3, but that's okay. 2 over 4 minus 2 cubed. 4 minus 2 is a positive number. That's all I care about. Positive over a positive is positive. This is greater than 0, so it's got to be concave up in that entire region, forever and ever. Cool. I think we've analyzed the heck out of this function. Yeah. Oh, I promised to zoom out on that to see if it looks like a straight line. So if we zoom out on this sucker, what does the function look like?
That's straight.
It looks like it's asymptote, right? If I take the asymptote out and the other one out, I guess it doesn't matter. It looks like 2 straight lines meeting. If I zoom way out, I can't even distinguish the vertical asymptote and the axis. Yeah, doesn't it look like y equals x minus 2? Yeah. Right. Is it exactly y equals x minus 2? No, there's that little fractional error hanging out on each side, but yeah, it looks like a straight line. Want to see another cute thing? Oh, of course you do. So we can have vertical asymptotes, we can have horizontal asymptotes, we can have slant asymptotes. Are there other kinds of asymptotes out there?
Absolutely.
Yes. You can have what's called a parabolic asymptote, right? And all I have to do to make a parabolic asymptote is raise the power of the numerator by 1.
That's scary.
So here's this function, right?
I hate that.
And if I zoom out on it, it's going to look like a parabola with this little weird hiccup in it.
That's cool.
Isn't that cool?
Why? Why?
Because think about it, as x gets big, this fraction gets smaller and insignificant, which means this part dominates the equation for big X. 'Cause this part's close to 0.
Like, is that just like a thing?
I don't know, it might have some universal significance. This is a big universe, who knows?
Giant tuning.
Okay, we got other stuff to do, so let's move on. Just to verify the error I made the other day, if the first derivative is undefined anywhere, it doesn't matter whether the original function was defined or not, we still need to consider that in terms of increasing and decreasing. It can't be a max or a min, so as far as the first derivative test goes, that number is not very useful because it doesn't help with a max or a min if the original function is undefined. However, just think of these two examples. Consider y equals 1 over x. Its derivative would be negative 1 over x squared. And the derivative is undefined for x equals 0, right? The original function, x can't be 0 either. However, if you consider the graph of that function, it looks like this. In this region, what's the concavity? Down. In this region, what's the concavity? Up. So you can't have a change in concavity across a value that isn't in the domain of the function. Okay. Does that always happen? No. Consider 1 over x squared. Its derivative, crazy pen. Its derivative would be negative 2 over x cubed.
Forgot the prime.
Prime, thank you. Both of these cannot have x equals 0. However, if you look at the original function, it looks like this. What's the concavity on the left? What's the concavity on the right? Yeah, it doesn't change over that value, so you just never know what can happen. Okay.
And that doesn't graph the original.
So technically, if the original function is undefined for a value, the derivative is going to be undefined for that value. It's not technically a critical number, because critical numbers apply to maxes and mins. However, the function can change concavity over that boundary. So we do need to consider it if we're looking for increasing and decreasing stuff. And calculus helps us figure that out. Okay, moving on. There's a problem from the homework I wanted to go over, which is this one right here. I think this was number 6, perhaps. 7? Okay, thank you. Number 7. This is a cute one. So let's find its derivative. F prime of x. Going to be 9 times 2/3. And then the power is going to be 2/3 minus 1. And usually with fractions, I slow down instead of doing that in my head. So let's see, 2/3 minus 1 would be 2/3 minus 3/3, which is negative 1/3 on a good day. Yeah. So 3 goes into 9, so we get 6 times x minus 3 to the power negative 1/3, which could also be written as 6 over x minus 3 to the 1/3. Now we could write it as the cube root, but most graphing devices don't have a cube root button. A couple do, but most don't. Does, most doesn't. I don't.
No, you can't.
So we need the 1/3 power.
I think there's an nth root.
Desmos has an nth root?
Yeah.
Oh, okay, cool. I'm going to leave the 1/3 power in here, but we could write it as a third root, right? So that's an option there. So what happens if we set f prime to 0? Oops, wrong place. Not 0 for x, but equal to 0. So then I'm going to get 6 over x minus 3 to the 1/3 equals 0. Well, the denominator can't be 0. So that means the numerator has to be 0. Well, 6 can't be 0, so there's no solutions to this part here. What's the other way to find critical numbers? Where the derivative is undefined. So the derivative is undefined, in this case, if the denominator is 0. So then I take x minus 3 to the power 1/3, and I set it equal to 0. If you cube both sides, then you get x minus 3 is 0, so x equals 3 is the only solution there. So 3 is a critical number. Is the original function defined at 3?
No.
Yeah.
Yes.
Yes.
Yeah, I can take the 2/3 power of 0. Yeah, so it turns out the original function 3 is in the domain. The domain of this function up here is all real numbers. There are no numbers that give it a problem. You can square any number, you can take the cube root of any number, you can subtract 3 from any number, you can multiply by 9 for any number. Yeah, so this is a critical value. Let's take a look at what's happening there. So number line 3 is a critical number. I need to consider what is f prime doing on each side of 3. So I need to pick a number to the left of 3, like
0.
0 or 2 works too. I'm going to pick 0. A number on the other side, go with 4. Sorry, I know you wanted 6. Both 2 people said 6. That was interesting. So that would be, I need to calculate 6 times, 6 divided by, right?
No.
Divided by 0 minus 3 to the power 1/3.
Yeah.
So that's the cube root of -3, which is, what is it?
Negative.
Yeah, it's a negative number, and that's mainly what I care about, that this thing right here is less than 0. So that means the function is decreasing over here, dropping. Other side, there's no guarantees. 6 divided by 4 minus 3 to the 1/3. Well, that's 1 to the 1/3, which is 1.
6.
So it's positive, greater than 0. Function is increasing on that side. Okay. Next, second derivative. Let's see, I ran out of room there, so we'll have to do it over here. For the second derivative, f double prime of x, I want to take the derivative with respect to x of the first derivative, which is 6 times, let's do the times version, x minus 3 to the power -1/3. It's an easier one to take the derivative of. So that's going to give me 6 times -1/3. Subtract 1 gives me -4/3, I think. I ignored the chain rule before, but I shouldn't have. What's the derivative of the inside here?
1.
1. Yeah, be careful about that. That was a faux pas on my part, although it didn't hurt anything. So let's see, what do I get? I get -2 times x minus 3 to the power -4/3. And I'm going to use the second derivative just to check what's happening here. Now I can see it's decreasing then increasing, so this ought to be a, nope, a min.
There-
Okay.
there's gonna be a min.
Decreasing then, it's a minimum. But let's just see what the second derivative says. If I plug the critical number into the second derivative, so f double prime of 3, oh, it doesn't help here, does it? Cool. I get 0, which is inconclusive. It doesn't tell me anything, which means go back and do the first derivative test. Fortunately, I did the first derivative test.
Does having that 0 mean anything for the function?
No, it just means the second derivative test fails.
Okay.
Oh, let me make sure I didn't lie again.
Wouldn't that be defined by 0?
That would be dividing by 0, so it's not 0, it's undefined. Thank you very much, William. That does not exist. Yeah. I'm going to have to get back to you on that question, Sally. Okay, is there significance to the second derivative being 0 or not being defined in this case?
When in doubt,
Is the
Google
graph-
it.
Yeah, I know what the graph looks like.
Okay.
Yeah. Does that help? I don't think that helps. Okay, I'll have to get back to you on that. All right, so what do we know? Let's see, some other things. Oh, let's test for concavity. If I were to plug in 0 into the second derivative, red for that. So f double prime of 0. If we plug in a 0 here, we're going to get a negative base to the 4th power.
It's a positive
That's a
number.
positive number. This is greater than 0. Oh, no. But then I'm multiplying by -2.
So it's a negative.
So it's a negative number. Okay. Less than 0. If we're less than 0, it is concave down. On the other side, if I plug in like 4, I have a positive denominator and a negative top. It's still less than 0. This thing is concave down on both sides of x equals 3. What about adding x equals 3? It's undefined. Yeah. It doesn't change concavity there, though, right? Sometimes this is an inflection point. This is not an inflection point. All right. So what do I know that's going on? I know that x equals 3 is an interesting number, but the function is defined there. I don't have any function values at the moment. My original function is f of x equals, was it 9 times x minus 3 to the power 2/3, right?
Mm-hmm.
Yeah. If I plug in 3 there, I get 0, don't I?
Yeah.
I'm squaring this parentheses, which means I never get a negative y value. So this thing is always above the axis. It's decreasing on this side. It's increasing on that side. And what's the concavity?
Down.
Always concave down. So it must decrease concave down into that point and then increase concave down away from that point. So the function does something like that. Okay. I know many of you have already asked your graphing thingy what it looks like. Let me catch up to you here. Close. We better call this g of x equals 9 times parentheses x minus 3 raised to the power. I think I need parentheses otherwise. Sure though. 2/3.
You don't need parentheses.
I would just have to carefully do division first, right?
Well, you can just do 2 pi by 3.
And it'll do it?
Mm-hmm.
Oh,
It kind of just treats it as its own little.
nice. All right. So look at what's happening in there. Okay. So this, there we go. So it is concave down when I zoom out. We saw that just a minute ago in the picture. It looks like it comes to a little pointy, sharp, pointy thing. That could be what's called a cusp. A cusp. So,
Here, you're killing me here, man.
why?
You keep adding things.
Math is full of things.
Like, I think I have this figured out, and you're like, wait, here's one more.
So a cusp happens on a function for a couple of things. First, if the derivative at that value does not exist, that's one thing that might lead to a cusp, but not always. The other thing that leads to a cusp is if the limit as x goes to that number from one side and the other of your function, if that goes to plus or minus infinity. So the derivative gets infinitely steep there. Then we have what's called a cusp. So let's just double check with our function.
Is that supposed to be f of x or f prime?
F prime of x. Yeah, the derivative function is what we're looking at. Yeah, that makes it really pointy. So for us, if we take the limit as x goes to 3 from the right or left, let's go to the right side, of ours was 6 over x minus 3 to the power 1/3.
That's going to be from 0, 1, 1.
Yeah, so let's see. The bottom is bigger than 3, right? So that means I have positive numbers in the bottom. and they're getting closer and closer to 0. 6 over something that's getting close to 0 gets close to infinity. Yeah, so the tangent lines are getting infinitely steep there. The tangent lines on the other side are also positive because of the concavity, and it's increasing over there. So on the other side, I'm going to get the same thing. So this is going to be equal to the limit as x goes to 3 on the left side of our derivative. I get the same thing, and that's what defines the cusp. Cusp is a pointy thing on the function. What's up?
Since it's to the third, would it be negative?
Oh, it's going to be...
Just looking at the graph, it looks like it's going to be going to negative. Indeed.
I think you mean, but because it's going left, not down.
Well, on the left side of 3.
Yeah, I see what you're
1/3
saying.
instead of 1/3.
Oh, I see.
Because of the 1/3 instead of.
Yeah, if I'm on the right side, there's a pot. Oh, yeah, I made a mistake there. Thank you. So let's see. It's not equal there. This one is definitely going to be negative infinity. You're right. Because these slopes are downhill on that side. So
But it doesn't
m is
matter.
less than 0, m is greater than 0.
But it doesn't matter since f of x can't equal positive or negative. So for this problem.
So this is just the slope of the function we're talking about here. Yeah. And for the cusp, we do, I'm pretty sure we want them to be opposite in sign.
Okay.
We invented the cusp. We need to get this better.
I'm 90% sure. I'll double check on that too and get back to you tomorrow or Tuesday. All right, let's take a look at another problem. I think we've beat.
in that problem, would f of x be not continuous?
The original function is continuous because there is no denominator here. So I can take the cube root of a number, whether it's positive or negative, right? And that's the only time I have a problem. So the domain here is all real numbers. Yeah, so the function exists and is defined there. Yeah. Yeah, so here I have an absolute min at the point 3, 0. Okay. Next, let's take a look at some other limits at infinity, which is the next section. New page, there we go. So consider the function 2x plus 3 over 5 minus 3x. Now, if anyone has the itch to cancel those 3's, don't do it. Don't do it.
You
can't.
Right, you can. Yeah, I'm just saying. Every once in a while, somebody does some illegal canceling. Just want to point out, those are not cancelable. All right, so what I want to do here is just look at a couple of things. Does this function have any asymptotes? Well, if the denominator is 0 and the numerator is not, it's going to have an asymptote. So are there any numbers that make 5 minus 3x 0? Yeah. If x equals 5/3, the denominator is 0. So if we were to take the limit as x approaches 5/3 from, let's say, the left side of our function. Oops. What's going to happen? So let's see. I have a number that's a little less than 5/3. And I have 5 minus that number here. 5 minus 3 times that number there. So now the 3's could cancel, right? Okay. So then I have a number a little less than 5. What's going to happen there?
And go to infinity. the bottom, or the whole fraction.
Yeah,
So it's gonna go to 0.
So for example, this could be like maybe x equals 4.9 thirds. That's a number a little less than, right, to the left side. So that means that I have 5 minus 4.9 in the bottom, which is a positive number. So I'm positive in the, oops, let's write that over here. I'm positive in the bottom. Now, the other thing is I'm trying to get close to 5 thirds, right? So that means this number is going to be close to 0. There's going to be a small difference. Okay. So I have a small positive number in the bottom. In the numerator, I plugged in something close to 5 thirds. I multiplied by 2 and added 3. So, you know, that's roughly going to be what? 10 thirds plus 3. It's some positive number. And it's fixed. It's a positive constant. It's getting closer to a positive constant, that is. What's happening overall here? Relatively fixed. Yeah, road poach is positive infinity. So as an x value approaches a fixed number, as y gets bigger and bigger and bigger, or heads toward negative infinity, this must be an vertical asymptote. I have 1 minute? Okay. So we can do a similar thing on the other side. I'm going to skip that. What I want to do next is look at a horizontal asymptote. Does this potentially have a horizontal asymptote? Yeah, because the degree of the top equals the degree of the bottom. So the trick there, one trick, is to divide by the highest power of x. Which is x in this case. So take our function, which was, what again, 2x plus 3 divided by 5, no, what was it?
Yeah, 5 minus
3x, there you go. So what I mean is divide everything by x. So this gets divided by x, that gets divided by x, that gets divided by x, and that gets divided by x. So I'm dividing top and bottom by x. In some places, so here, 2x over x, that's just 2, but I have plus 3 over x. Here I'm stuck with a 5 over x minus 3. And what am I letting x do here? Well, I'm looking for a horizontal asymptote, so that means I'm looking to see what happens as x gets big. What's 3 over a huge number? Essentially 0, right? So what's happening is that number in the limit is going to 0. 5 over a huge number is getting close to 0. So I have 0 minus 3, and so I get the limit is 2 over negative 3. So in general, what's going to happen is it's going to be the ratio of the coefficient, the leading coefficients. The leading coefficients, if you look back at the original, will be the things multiplied by the x. So 2 over negative 3 in that case. And that's how you find horizontal, horizontal asymptotes. All right, we're out of time for fun with math. Section 5, shapes of graphs. Homework is due tonight. 4.5 is due tonight, correct.
Oh, this is 4.6.
This is 4.6. This isn't due till Tuesday, I think.
Yes. So for the test or the final, is the title over everything you learned, or what is the section?
Finals over everything. I'm going to start working on a sample final this weekend.
Did we take this test before we take the final, or is this in the final,
Oh, yeah,
not a
right.
test?
I was looking at the calendar.
No.
There's no
final.
separate test on this
Okay.
stuff.
I was also going to ask, so like,